Hey everybody. Well, you can see I am back in my usual surroundings, but I have a slightly different voice, and that's what happens when you get COVID. So, that's why I might sound a little bit differently. So we are heading toward the home stretch. We're going to continue with hypothesis testing, and only this time we're going to be working with two samples instead of one sample. And we're going to have one presentation here on independent samples and one on dependent samples. And you're going to see these are very different things that we're testing. Let me just tell you, independent samples they come from different populations, with different means and different standard deviations, and these samples are not related, so there shouldn't be any connection between the two of them, and they might have different sizes. Dependent samples are quite different. Dependent samples, samples are dependent, then each member of one sample corresponds to a unique member of the other sample. And that means that in particular, two samples are dependent, they have to have the same size. Okay. And a lot of these times, one example of a dependent sample would be maybe like a before and after measurements, okay, like after, a diet or something like that. Here's two basic examples. So in this first example, we take the IQ scores of 50 residents of Illinois, and then for our second sample, we take the IQ scores of 50 residents in Florida. Those are examples those are independent, right? And if we could actually, to have 50 residents in Illinois and 70 residents in Florida, that would definitely be independent, right? Okay, but presumably there's no connection between the residents of these 50 people in Illinois and the 50 people in Florida. Then as long as that's happening, these are independent. However, in this next example, if we have take the weights of 30 people before a diet program and the weights of the same 30 people after the diet program, then those would be dependent, certainly dependent. And then we would take this, and maybe if we wanted to test if this that diet works, we really would like to compare the mean of this sample and the mean of this sample, and more importantly, the differences in the weights. And that's what we're doing when we work with dependent samples. We're actually going to be looking at the differences of these of the data in the two samples. But for this section, we're going to be focusing on independent samples. So like we're going to say, well, you might be asking, are men smarter than women, or are women smarter than men? That type of thing. Okay, more particularly, we're going to be looking at two populations with their own means and standard deviations, and then we'll be taking our first sample as a subset of population 1, our second sample is a subset of population 2, and of course these samples will have their own sizes and their own means. We're going to see if the populations are normally distributed, or both the sample sizes are at least 30, the central limit theorem is going to kick in. And as a result of the central limit theorem, we have this new random variable, which is defined as x1 bar minus x2 bar. This is a random variable, right? This is going to be a single number. It's an outcome of this experiment of taking these two samples, calculating their means, and subtracting them. This is a random variable is going to have a normal probability distribution where the mean is mu1 minus mu2, and the standard deviation is given by this complicated square root, the square root of sigma 1 squared divided by n1 plus sigma 2 squared divided by n2. There should be a 2 there. All right, so so that the central limit theorem says that's what must happen. If you want to see the proof of that, I'd suggest you take a higher level statistics class. as in terms of hypothesis testing, what can we do with this? Well, for this lesson, the claims that you'll be evaluating or testing will be one of these 6 forms, right? Mu1, it would be a statement about mu1 and mu2, and you're just comparing them. And you're just saying, a claim will either say mu1 is less than or equal to mu2, or greater than or equal to, or strictly less than, or equal or not equal. And depending on this case, if you have, if your null hypothesis is this, again, the null hypothesis must have equality in it, so these are the only 3 possibilities for the null hypothesis. And if the null hypothesis says mu1 is less than or equal to mu2, then an alternative, the extreme case would be where mu1, where a mean from population 1 is greater than the mean from population 2. And that's why the extreme values of your sample standardized statistic would be over here. So here you would be taking a right tail test. And if you're not quite sure about how that works, this would be, you can just say mu1 minus mu2 is greater than 0. So you think about this difference, and this difference would be positive. So a positive difference would be unusual if we assume this is true. So that's why we have a right tail test. And then in here we get the opposite. When if we assume that mu1 is greater than or equal to mu2, then the opposite is this. And this would mean that mu1 minus mu2 is less than 0. So the unlikely values would be negative. And then here we have equality, so we have a 2-tailed test here. All right, and the standardized test statistic is, we're going to see what it is. Basically, it's based on what we just said in the previous slide. So the guidelines for hypothesis testing are these 7 steps. We have to verify the samples are random and independent. We also have to verify, in this case, that sigma 1 and sigma 2 are both known. That is, the population standard deviations for both populations are known. And that the populations are either normally distributed or the sample sizes are both at least 30. Then, as before, we state the null hypothesis and the alternative hypothesis. We identify the claim. And then we specify the level of significance, alpha, which will be given to us. Then we, based on which case we're dealing with, we determine the critical values of the boundaries of these regions, shaded regions, and then we determine the critical values and the rejection regions. And then we compute the standardized test statistic, okay, which is this stuff right here. And what this is, because we said that x1 bar minus x2 bar has a standard normal distribution, where the mean is this and the standard deviation is this, then this whole expression, this whole fraction has a standard normal distribution. Okay, so that's why we can use the standard normal distribution. One thing here is, well, how do we know what this is if we don't know the values of mu1 and mu2? Well, remember, we just need to know what the difference is. And we know that we are assuming something. When we're assuming, let's say, mu1 is less than or equal to mu2, that's the same thing as saying that mu1 minus mu2 is greater than or equal to 0. And so we could take this, because we're assuming it's at most 0, we can assume that this is equal to 0. And just by the fact, as before, if mu1 minus mu2 is actually less than 0, it's not going to change the result of our hypothesis. Okay, if it's actually less and we're rejecting it, well, we're still, if it's negative, then we're still going to reject it. Okay, so that's why we can basically take this to be 0. Okay, because we are assuming something, and that we're assuming the possibility that mu1 minus mu2 could be 0. And so we just need this. So a lot of times this is really just going to be x1 bar minus x2 bar over this square root here. And then we just either reject or don't reject the null hypothesis, depending if this number is in the rejection region. And then we interpret our decision into the context of the original claim. So we're either going to be rejecting or not rejecting or supporting or not supporting the claim. All right. So this is how the game is played. And in the next video, we're going to do a few examples and see how this actually is put into action. So I'll see you then.